Section 1.4, Library of Functions and Piecewise Defined Functions. So let's first start talking about the constant function. The constant function is the function f of x is equal to b. b has got to be a real number. Remember that this is just going to be a horizontal line that passes through the line b. Its domain ends up being all real numbers, and remember that if we're trying to find that domain, we can go from left to right, and we'll see that we're touching everything on the graph, and so the domain is all real numbers. But when we want to discuss the range, the only output values that we have here are the value b, whatever that may be. And so the range we're going to write like this. That is, this is read the set, that's the curly braces, y such that, that vertical line is read such that y equals b. Y such that y is equal to b. Really, this just says that the range is the value b. Then we want to know where is this function increasing, and it increases nowhere. Where is this function decreasing? Nowhere. And then it's constant everywhere. Where its intercepts are going to be 0b unless it ends up being f of x is equal to 0, in which case the intercepts are actually the entire x-axis. Is this function even, odd, or neither? Notice that it does have y-axis symmetry, and since it's a function, that means that it's an even function. Now to talk about the identity function, that is f of x is equal to x. Now we want to discuss its domain, but notice that if I move from left to right with my line that's vertically infinite, it touches everything on the graph, and therefore my domain is from negative infinity to positive infinity. That is all real numbers. The range, if we start from the bottom and we see with our horizontal line what we touch everything. That is, the range is all real numbers, or negative infinity to positive infinity. Then we want to know where this function is increasing, and notice that if we move left to right, we do rise, therefore it's increasing from negative infinity to positive infinity. Then we want to talk about where is this function decreasing, but it doesn't decrease at all, so it's not decreasing. Then to discuss the intercepts, specifically it has the one intercept at the origin 0, 0. And then we want to talk about symmetry. Does it have any symmetry, specifically y-axis symmetry? But notice not y-axis symmetry, it's not mirror images across the y. But if we rotate it 180 degrees, we will get the same graph we started with, and so this does have origin symmetry, and since it's a function, that means it's an odd function. The square function, that is f of x is equal to x squared, it has a domain of all real numbers, or from negative infinity to positive infinity. Then to discuss the range, notice if we start from the bottom and move our way up, when do we first start touching values on the graph? And that's at 0. 0 is a real point, so it's 0 inclusive with a square bracket, all the way to infinity because it goes up forever. Where is this function increasing? Specifically, it's going to be increasing from 0 to infinity. We will include that 0 with the square bracket because that point does exist. Then where we ask where it's decreasing, and that is all of this stuff up to 0. Since 0 is a real point, then we will include it with a square bracket, so it's decreasing from negative infinity to 0. Now we want to know where are the intercepts. Specifically, they are the origin point 0, 0. Then we want to talk about the symmetry. Notice that it does have y-axis symmetry. Then, since it's a function, we would say that that's an even function. The square root function, f of x is equal to the square root of x. First, the domain. We start at 0. It does exist, so that's a square bracket, and then it continues up to infinity. Then for the range, similar game, but from the bottom, we first start touching values for y on 0. It is a real value, so it's included with a square bracket, and then it continues up forever. Then where is this function increasing? It's increasing from 0 to infinity. That is, we will include the 0 because it really exists as a point. Then where is it decreasing? Well, it's decreasing nowhere. And where are the intercepts? Specifically at the origin 0, 0. Then we want to talk about symmetry, but it does not have y-axis symmetry and it does not have origin symmetry, so it's neither even nor odd. The cubic function, f of x is equal to x cubed, that is this shape. The domain here is all real numbers. If we move from left to right, we'll see that we touch everything on the graph. The range is the same. Start from the bottom. We will touch everything on the graph. That's going to be from negative infinity to positive infinity. Then we want to know where is this function increasing, and it's actually increasing for its entirety. So we're increasing from negative infinity to positive infinity. And since we're increasing everywhere, we're decreasing nowhere. Then the intercepts are specifically the origin point, 0, 0. And do we have any symmetry? Notice that we do not have y-axis symmetry, so therefore it's not an even function. Then if you were to turn it upside down or rotate it 180 degrees, do you get the exact same function that you started with? And the answer is yes. So this function does have origin symmetry, and since it's a function, it is then an odd function. Now to talk about the cube root function, that is f of x is equal to the cube root of x. What is the domain? Start from the left. Notice that we are always touching some value on the graph, and so the domain is from negative infinity to positive infinity. Then for the range, starting from the bottom, we increase until we get to our first point, but we're always touching points, and so our range is from negative infinity to positive infinity. That is all real numbers. Then where is this function increasing? Notice that as we start on the function, we are always rising as we move from left to right, so this function is increasing from negative infinity to positive infinity. Then, because it's increasing everywhere, it's decreasing nowhere. For the intercepts, we just have the origin 0, 0. And then we need to discuss symmetry, but this does not have y-axis symmetry, so it's not even. But if you rotate this graph 180 degrees, notice that you will have the exact same graph that you started with, so thus origin symmetry for a function implies that it's odd. Next we have the reciprocal function, that is f of x is equal to 1 divided by x. This one's an interesting function and a few things to talk about before we go further. That is, the reciprocal function has something called an asymptote. Remember that when we want to find the domain for this function, we have an issue, and that is we cannot divide by 0. And since we cannot divide by 0, we know that this value 0 is kicked out. And so our domain goes from negative infinity to 0, exclusive, that is parentheses means 0 is kicked out, union, kick out the 0 all the way to positive infinity. If you do this visually, you start on the left and you ask, are you touching values on the graph? And way over at negative infinity, you're touching values. And you continue to touch values until you get to 0. Now, this is the tricky part. If you don't know this, it may not make a lot of sense. The reciprocal function has this thing called an asymptote. It actually has two of them. An asymptote is just an imaginary line where the graph approaches it. And so that is, if you were to follow this piece of the reciprocal function, this thing keeps getting closer and closer and closer to this asymptote, but it never touches it. And so as we approach 0, this thing goes down forever. Similarly, as we come from this side, as we approach 0, this thing increases forever, but it never actually gets all the way over here on the y-axis. And so that's what an asymptote is. It's something where a graph approaches it but never touches it after some point. Well, there's also another asymptote that you might not be aware of, and that is the x-axis. And so there's this other asymptote where if we follow this graph, it approaches the x-axis, and as we keep going, it'll get closer and closer and closer, but we'll never actually touch the x-axis. Similarly, this part will do the exact same thing. It's going to approach the x-axis, but it will never actually touch it. So when we try to find the range, and we ask ourselves, when do we start touching values on the graph? The answer is we start all the way at negative infinity, and we're touching values on the graph. We have values until we get to the x-axis. And at the x-axis, that is 0, there's no defined values. And so the range for the reciprocal function is exactly the same as the domain, that is from negative infinity to 0, where we do not include the 0, union 0, not including, up to infinity. Then we want to know, where is this function increasing? Notice that it's not increasing anywhere. This is falling as we move left to right, and this one is also falling as we move left to right. You just have to pick up your pen to get from the end of this piece to this piece. So that is, this function is decreasing from negative infinity to 0, but we do not include 0 because 0 doesn't actually exist on this graph. And then we have to start back up on the right side of 0, but we don't include it either, so that's a parentheses, and then we start following that graph all the way to infinity. Then we want to talk about intercepts, but there are none. Because of the asymptotes and the way this graph is shaped, we don't actually cross the axes. Be aware that some reciprocal functions may have intercepts, even if they have asymptotes, but we'll talk about that when we get to rational expressions. Is this function even, odd, or neither? Well, notice that we do not have y-axis symmetry. But we do have origin symmetry. That is, if I rotate this image 180 degrees, it is the exact same image that I started with, which is an odd function. The absolute value function, that is f of x is equal to the absolute value of x. First, discuss the domain, that is what values occur on the x values, and that is everything. So the domain is all real numbers, that is from negative infinity to positive infinity. Then we want to discuss the range, but since we have the graph visually, we can start from the bottom and move our way up until we touch our first values. Our first values are touched at the origin 0, 0, so that y value is 0. It does exist, so we do include it, and then we continue all the way to infinity. So our range is from 0 to infinity, including 0. Then we want to know, where is this function increasing? It's increasing from 0 to the right, We will include that 0 because it's a real value with a solid dot here. And then we want to discuss decreasing. Decreasing is from negative infinity up to 0, and since that's a solid dot, we will include it as well. Then we want to discuss the intercepts, but there's only the origin intercept, that is 0, 0. Then we want to talk about its symmetry. Notice that it does have y-axis symmetry. It mirrors across the y-axis. And since it's a function, it's then an even function. If we rotate it 180 degrees, we do not get the same thing we started with. Thus, it's not origin symmetric and not odd, only even. So now we want to graph the function f of x is equal to 4x cubed. Just to keep us on track, remember that we kind of know what x cubed functions look like. They look like this. So just as a quick sketch, I know that's what it looks like, but I need an accurate representation of this graph. Well, how can we find it? Well, we can use what's called a t-chart. So a t-chart says pick some x values and plug those into the function, and we can evaluate it. And then we can plot the ordered pairs that we find. So I'm going to pick some nice easy values to calculate. How about 0? 0 is a good value to calculate. And then I'm going to also pick negative 1 and positive 1. We'll plug these values in. That is negative 1 quantity cubed. 4 times negative 1 quantity cubed. That's really 4 times negative 1, or negative 4. Then 4 times 0 cubed. That's just 0 times 4, or 0. And then 4 times 1 cubed. That's just 4 times 1, or 4. And so I got 3 ordered pairs. Negative 1, negative 4, 0, 0, and then 1, positive 4. And then I just need to sketch the graph. Now this is a sketch, so everything except for the solid dots that I've actually found is just going to be close. But I claim that the solid dots will be correct. Now we have a reciprocal function. Once again, remember that that reciprocal function is going to look something like this. Now there are some adjustments that actually occur, and so notice that since this is times 6, this is actually a vertical stretch. And so this thing is going to get taller and skinnier in a way. But the asymptotes will still be the same. Now, because of the interesting shape of this reciprocal function, I claim we should probably pick 6 values, 3 for this piece on the left and 3 for this piece on the right. So we need to pick some values. Let's pick some on the left-hand side. Well, 0 is not going to be on there. We know that doesn't exist. And so why don't we pick values like negative 1, negative 2, negative 6. Now I've chosen these values for 2 reasons. First off, because I think they'll be pretty easy to calculate, but I'm also considering the fact that this is a fraction. And so I'm picking numbers that will divide 6 nicely. 6 divided by negative 6, well, that's going to be negative 1. And so there's negative 1. And then 6 divided by negative 2, that's going to be negative 3. Then I have 6 divided by negative 1. 6 divided by negative 1 is negative 6. And so at this point, we can sketch this part if we so desire. That is, at negative 6, I have negative 1. At negative 2, I have negative 3. At negative 1, I have negative 6. And remember that I have that asymptote that I'm approaching, both on the y-axis and the x-axis. And so there's that piece. But remember, it's just going to approach the y-axis and approach the x-axis. Well, now let's pick some values for the right-hand piece. Well, once again, I'm thinking about 6 divided by whole numbers that give me a whole number. So I'm going to try 1, 2, and 6. 6 divided by 1 is 6. 6 divided by 2 is 3. 6 divided by 6 is 1. Then I can graph these points. I have 1, 6, 2, 3, and 6, 1. Then once again we have this asymptote that is the y-axis. And then we also have this asymptote that is the x-axis, and that is it approaches it but never touches it. And so there we are. Piecewise defined functions are called piecewise defined functions because they are functions defined by different equations on different parts, that is, pieces. Specifically, those pieces will be defined on different domains. That's what makes a piecewise defined function. So let's consider this function. If f of x is equal to 2x minus 3, it's only going to look like 2x minus 3 when x is between negative 2, including negative 2 because of the equality, and less than or equal to 3. And then it'll also look like x cubed minus 3 anytime x is between 3 and 5, or including 5. So now we want to know which equation would you look for the y-intercept? Well, remember that the y-intercept occurs when x is 0. So if I were to plug in x as 0, piecewise defined functions actually give me the instructions on where to plug in values. So if I want to plug in 0, I go to the instructions. The instructions are here. Notice, where does 0 live? 0 lives between -2 and 3. So that is, the instructions are telling us that 0 gets plugged into 2x minus 3. And so that is 2x minus 3. So f of 0 ends up being 2 times 0 minus 3. 2 times 0 is 0. 0 minus 3 is minus 3. Now, just for the sake of more practice, let's calculate f of 1. Remember, we need to follow our instructions. 1 gets plugged in, but we're told where to plug it in. Notice that 1 lives between -2 and 3, so it gets plugged into the top portion. So this is 2 times 1 minus 3. 2 times 1 is 2. 2 minus 3 is -1. Now to calculate f of 3, once again, follow the instructions. 3, go up here. Well, notice I have a 3 at the bottom and up here. But this one has the equality. So the 3 gets plugged into the top piece, 2x minus 3. So that is 2 times 3 minus 3, or 6 minus 3, which is 3. Now for f of 5, follow the instructions. Go up here, look for the instructions. Is 5 between -2 and 3? It is not. So notice that 5 is 5 between 3 and 5. Well, because there's an equality, it goes right here. So we're going to plug it in. That is 5 cubed minus 3. 5 cubed is 125 minus 3. 125 minus 3 is 122. Find the following. Now I'm going to claim that graphing this first may be the most useful. There's several ways to graph it. Namely, you can do what's called a graph and erase. That is, you can graph both pieces and then erase the parts where they're not defined based on this domain instruction. Or you can follow the domain instruction and then pick a t-chart and plug in values. But because of the way this is defined, I'm just going to graph them and then notice that it doesn't exist at 0. So we have a function f of x is equal to x, that is the identity function, y equals x, as long as x does not equal 0. So that is, at 0, the value does not exist, so I need to put a hole there. Then the rest of this thing looks like y equals x, that is, the y-intercept of 0 with a slope of 1, and so it looks like this and like this. So that's this top piece. Everywhere but 0, it looks like the identity function. But then we need to discuss what happens at 0. Well, at 0, we get the output 5, so we just plot that. 0, 5 goes right here. Solid dot right there. So that's our function. Well, now we need to find the domain. But notice you could use our vertical line from way over here and say, are you touching the function? The answer is yes. And is there ever a point you're not touching the function? This is questionable, but because of the solid dot, it's included, and so this domain is actually all real numbers, or from -infinity to +infinity. But then we need to discuss the range. So take a horizontal line that stretches forever in both directions and move up the graph and ask yourself, am I touching values on the function? And the answer is yes, until you get to 0. At 0, there's a hole. And so that is, the range is going to go from -infinity up to 0. Because 0 isn't really included, we don't include 0, that is with the parentheses. Then we pick back up right after 0, so union, start again at 0, and then move on to infinity. So those are all the values that get output from the function. Then we need to find the intercepts, but notice there's only one intercept, that is that point, 0, 5, and so that's our only intercept. And since we've already graphed it, we're done. Now we want to find the same things. Once again, if you so desire, we can graph it from the start. But for this one, I'm going to use a t-chart. And I'm going to need 2 t-charts because I have 2 pieces. So my first piece is going to be, I pick x's, and they're going to be plugged into this top function, 3 plus 3x. We'll talk about how to pick those values in a moment. Then the other piece, we're going to pick the x values, plug them into x squared. Now, how do we choose the values? Well, for the top piece, 3 plus 3x, we have a set of instructions here. If x is less than 0, it goes into 3 plus 3x. Well, because 0 is on the inequality, or if it was equality as well, we would want to plug it in. So I'm going to pick that value that's listed in that inequality as a value to plug in. But I want to go ahead and make note that is because I'm lacking equality, I'm going to use an open circle because it doesn't actually exist at that point. Then I need to pick values to the left of x. Well, why not pick two more? How about we plug in -1 and -2? Well, plugging them in, that's going to be 3 plus 3 times -2. -2 times 3 is -6. -6 plus 3 is -3. Then if I plug in -1, that's 3 plus 3 times -1. -1 times 3 is -3. -3 plus 3 is 0. Then plug in 0. 3 plus 3 times 0 is 0 plus 3, or 3. So now to graph what we have, remember that this open circle that I was talking about will be on that ordered pair 0, 3. So at 0, 3, I do have an open circle. That point doesn't actually exist. Then I graph my other ordered pairs. -1, 0. -2, -3. Then, because I know that 3 plus 3x is a line, I can just connect these solid dots to my open circle because I know that this function really exists to the left of 0. And so this function looks like that. Now for the other piece. Well, it looks like x squared. Remember that x squared is parabolic. It looks like this. And that's going to exist from 0 equal to 0 and to the right. So for the x values I choose, I'm going to definitely choose the value in the inequality, 0. But for this one, I'm going to remember that because it's equal, it's going to be a solid dot. Then I'm going to pick two more values just for the sake of it. How about we pick 1 and 2? Well, 0 squared is 0, 1 squared is 1, 2 squared is 4. I'm just plugging it into that function there. Then plot these ordered pairs. I have a solid dot at 0, 0. Then I have a solid dot at 1, 1, and a solid dot at 2, 4. And because I know what this parabola looks like, I know that the shape is about like this. Then we want to know what is the domain of this function. Well, the domain of this function, start on the left-hand side and ask yourself, when do you start touching function values? Well, all the way over at -infinity. And then as I move towards the left, I do have to be a little bit concerned because of this open circle, but because of this solid dot, it gets filled in, and so there actually is a value that exists there. And then I continue and I see that I have values forever. And so the domain here is from -infinity to positive infinity. Then when discussing the range, similar, but start from the bottom. Start from the bottom, the first values we touch are way all the way down at -infinity, and then I continue to touch function values until, well, I always do. And so the range is also -infinity to positive infinity. Then to find the intercepts, we've actually found them in our t-chart. That is, notice when we plug in x equals 0, it's actually getting plugged into x squared, and so we do get the origin point 0, 0, which is, of course, that point. We also see that we have an x-intercept. And so if I set this function equal to 0, you could solve both pieces equal to 0 and see which one falls into the correct domain. Let's actually try that real quick. So if I say 3 plus 3x is equal to 0, well, what do I get? -3 minus 3. 3x equals -3. Divide by 3, divide by 3. X is equal to -1. Check and notice that -1 is in these instructions. And so since it is in these instructions, I claim that we found another x-intercept, specifically the value -1, 0. Now given f of x is equal to the absolute value of 2x if x is between -1 and 0, including -1, and it looks like x cubed if x is greater than or equal to 0. So I'm going to start by graphing it again. I'm going to use a t-chart, some x values, another t-chart for the other piece, pick some x values. If I had 3 pieces, I'd have 3 t-charts. Well, for the absolute value of 2x, we know that that's going to be true from -1 to 0, and then we might want to pick a value in between. And so for that one, we're going to evaluate it at the function values for absolute value of 2x. Well, the values that we must plug in are -1 and 0. -1 and 0. Now for the sake of it, I'm going to go ahead and pick another value in between because really 1/2 works very nicely in this function. So -1 plugged in here, that's 2 times -1 in absolute value. That's really -2 in absolute value, which is really +2. Then let's plug negative 1/2. So then the absolute value of 2 times negative 1/2 is going to give us the absolute value of negative 1, but the absolute value of negative 1 is just positive. Then we plug in 0. 2 times 0, absolute value is 0. The absolute value of 0 is, of course, 0. Now, be a little bit careful because these things, these inequalities or equalities, correspond to solid dots and open circles. Equality is a solid dot. So that means that the ordered pair, negative 1, 2, we have a solid dot. The strict inequality is an open circle, and so we know that the ordered pair 0, 0 is actually an open circle. So, for the point negative 1, 2, we know that we have a solid dot. Then at the point negative 1, 1, that actually exists. At the point negative 1/2, 1, we know that it actually exists, so that's about right there. And then we have the next ordered pair 0, 0. But be careful, because the point 0, 0 must be an open circle, because it is not equal. So we can connect these, and we see that we do not continue because these inequalities are really trapping that x value between negative 1 and 0. Then we want to graph x cubed. Now, for the sake of remembering, I know that x cubed looks something like this. But we can still pick values, and so let's pick them. Let's pick the value that's in the inequality, that is 0. And then let's remember that that's a solid dot. So we have a solid dot here. Then we need to pick some other values to the right of 0 where x's are bigger than 0. So how about 1 and 2? Then let's plug those in. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So I have 3 ordered pairs to plot. The first one being 0, 0, which is, remember, a solid dot. So it actually is going to fill in that open circle. This just happens sometimes, and that's okay. Then we have the next ordered pair 1, 1. Then we have the next ordered pair 2, 8. And I need to make this kind of look like the cubic function, which does look something like this. Now we can discuss the domain of this function. You can do this in one of two ways. You can consider what's written in the inequality form and convert that to the domain, or you can just look at the graph and notice that as we come to the left, the first values we hit are negative 2, and it really does exist, so it's a square bracket. And then we filled in this open circle with a solid dot, so that one's good, and then it continues forever to the right, so that's from negative 2 to infinity. Then we want to find the range, to start from the bottom and move our way up. The first value that shows up for the y values is the point 0. It is a solid dot, so that's included. And then we continue all the way up to infinity. Then to find the intercepts, notice that the only one we have is the origin, which we did calculate up here as a solid dot. And so the x-intercepts and the y-intercept are both the origin point 0, 0. An adverse market delivery charge rate depends on the credit score of the borrower, the amount borrowed, and the loan-to-value ratio, LTV for short. The LTV ratio is the ratio of amount borrowed to appraised value of the home. For example, a home buyer who wished to borrow $250,000 with a credit score of 730 and an LTV ratio of 80% will pay 0.5% or 0.005 of $250,000. Which is really $1,250. This table here, this is the table below, that's really above, shows the adverse delivery charge for various credit scores and an LTV ratio of 80%. Now, why is this all thrown up here? This is going to be a real-world example of a piecewise defined function. Essentially, if you want to borrow some money for a house, then maybe they're going to use a chart like this. Based on your credit score, they're going to charge you some amount of the money that you want to borrow. And we can see that if the person that has a credit score of 730, which falls into this category here, they're going to have a charge rate of 0.5%. Well, just a quick reminder, 0.5%, percent means per 100, so that's really 0.5 divided by 100, which is really going to be 0.005. So the number that we need to calculate with is 0.005. But since that's the charge rate, so we multiply that times the amount that's going to be borrowed, which is in this case $250,000, and then we get the value after that multiplication of 1,250. So now what we're going to do is we're going to construct the function where C is the output or the cost based on S, where S is the credit score and C is the average market delivery charge. Now specifically we're going to do it based on a $300,000 loan, and with the 80% ratio means we're just going to use this chart above. And so for the first one, if I want to know what goes here, I need to first consider that they have a credit score of less than or equal to 659. So that's this part. Then that was a 3.75 charge rate, which means that it's a 0.0375 rate times that $300,000. And if we multiply that together, we're going to get 11,250. And that's how much they would have to be charged if they're going to borrow $300,000, and that's their credit score. Next, if the credit score is between 660 and 679, we're going to use this. Well, that's a 2.5% charge rate, so that is 0.025 times 300,000, which is going to give us 7,500, and that's how much that person would be charged for a $300,000 loan. Now for the credit score of between 680 and 699, we're right here. So that's a charge rate of 1.5% or 0.015. 0.015 times 300,000, that's going to give us a value of 4,500. Then when the credit score is between 700 and 719, this is the charge rate. So that's going to be 1% or 0.01 times 300,000. Which is going to leave us with 3,000 being the charge rate. Then when the credit score is between 720 and 739, we're using this charge rate 0.5%. That is 0.005 times 300,000, which really gives us $1,500. That's the charge rate. Then for a credit score of 740, we use the charge rate of 0.25% or 0.0025 times 300,000, which is going to give us a charge rate of $750. Now we want to know what is the adverse market delivery charge on a $300,000 loan with an 80% LTV ratio for a borrower whose score is 724. Two ways you can do this. You can look at that piecewise defined function that we just made and you can answer the question immediately. We've already calculated all those values. Or you could calculate it again. If the score is 724, that is in this one, and this one, we have a rate of 0.5% or 0.005 times the $300,000, and that's going to give me a value of $1,500. But that matches exactly what we just found in the previous piecewise defined function. Now if we want to know what the delivery charge is when the score is 689, then we find 689. 689 lives here. That is a 1.5% charge or 0.015 times 300,000, which is going to give us a value of 4,500.